Have you ever considered the possibility of an asteroid colliding with Earth, resulting in catastrophic consequences? Some of the most brilliant minds today are focused on finding ways to help humanity deal with such a disaster. One notable individual is Elon Musk, who is taking personal steps to ensure our survival in the face of such a catastrophe. However, NASA is also actively contemplating the same problem and issuing warnings about potential cosmic collisions with asteroids. To prevent such occurrences, NASA is developing a system known as DARTS. What exactly is DARTS, and how does NASA plan to employ it in order to prevent asteroids from colliding with Earth? Join us as we delve into NASA's chief's grave warning about the possibility of an asteroid impact. Asteroids. These massive celestial objects that have been popularized in films for their ability to cause devastation and chaos upon colliding with Earth. But is it true that asteroids can strike our planet? Before we address this question, it's important to understand a few key facts about asteroids. They are rocky objects that orbit the Sun, but are too small to be classified as planets. They are also referred to as planetoids or minor planets. There are millions of asteroids varying in size, ranging from several feet to hundreds of miles in diameter. In terms of total mass, all the asteroids combined weigh less than Earth's moon. These asteroids primarily exist within 3 regions of the solar system. The majority of asteroids populate a vast ring situated between the orbits of Mars and Jupiter. This belt is home to over 200 asteroids with diameters exceeding 60 miles or 100 kilometers. Additionally, scientists estimate that the asteroid belt contains between 1.1 million and 1.9 million asteroids larger than 1 kilometer, 3,281 feet in diameter, along with countless smaller ones. Not everything found in the main asteroid belt can be classified as a typical asteroid. In fact, there is a series of objects that were initially considered asteroids but turned out to be dwarf planets. Over the past decade, scientists have made this discovery. Additionally, they have identified another category called main belt comets. These are small rocky objects that possess tails. While some of these tails are formed when objects collide with asteroids or when asteroids disintegrate, others may actually be comets in disguise. Asteroids, in essence, are remnants from the early days of our solar system's formation, which occurred approximately 4.6 billion years ago. During that time, the presence of Jupiter prevented the formation of larger planetary bodies in the region between Mars and Jupiter, resulting in collisions and fragmentation among the existing small objects. This led to the formation of the asteroids we observe today. Most asteroids have irregular shapes, although there are a few notable exceptions. For instance, Vesta, with a diameter of approximately 285 miles or 460 kilometers, boasts a large impact crater. As asteroids travel along their elliptical orbits around the Sun, they also undergo rotational motion, sometimes exhibiting erratic tumbling. Interestingly, more than 150 asteroids are known to have small companion moons, and some even possess 2 moons. There are also binary or double asteroid systems, where 2 asteroids of roughly equal size orbit each other, as well as triple asteroid systems. Near-Earth asteroids, commonly referred to as NEAs, orbit the Sun at a similar distance to Earth. These objects are further classified based on how their orbits compare to Earth's. For instance, Amor asteroids have orbits that approach Earth's path but remain exclusively between Earth and Mars. On the other hand, Apollo asteroids have Earth-crossing orbits but spend the majority of their time outside Earth's path. Astronomers have also identified a specific group of NEAs known as potentially hazardous asteroids, or PHAs. These are rocks that come within approximately 4.65 million miles or 7.48 million kilometers of Earth's orbit and have a diameter larger than about 500 feet or 140 meters. Scientists have discovered over 27,000 NEAs, with nearly 10,000 of them having diameters exceeding 500 feet. So, the question remains, are we truly at risk of a collision with an asteroid? The short answer is yes. Since Earth's formation about 4.5 billion years ago, asteroids and comets have regularly impacted the planet. An asteroid larger than 1/4 of a mile in size has the potential to cause a global disaster. Researchers estimate that such an impact would release a significant amount of dust into the atmosphere, resulting in a nuclear winter-like effect and severely disrupting global agriculture. Smaller asteroids have the capacity to destroy cities or generate devastating tsunamis. Space rocks smaller than 82 feet or 25 meters tend to burn up as they enter Earth's atmosphere. However, in 2013, an asteroid entered the atmosphere over the Russian city of Chelyabinsk, creating a shockwave that injured 1,200 people. This particular space rock was estimated to be around 65 feet or 20 meters wide upon entry. This raises the question of how we can protect Earth against future potentially catastrophic asteroid impacts, or whether we are simply helpless, awaiting the outcome of an asteroid on a collision course with our planet. Elon Musk is deeply invested in the idea of transforming Mars into a habitable environment. His rationale stems from the belief that a portion of humanity should establish a presence on Mars to ensure survival in the event of an asteroid catastrophe that wipes out life on Earth. Musk envisions a self-sustaining community of 1 million people on the Red Planet and is actively developing a spacecraft to transport volunteers to Mars. However, executing Musk's plan necessitates substantial funding and remarkable technological advancements to make it a reality. While Musk's approach focuses on relocating to avoid a potential asteroid impact, NASA takes a different approach by intercepting the asteroid as it approaches. This strategy is known as the Double Asteroid Redirection Test, DART. But how does DART work? In simple terms, sometime between late September and early October of 2022, the DART spacecraft, weighing 1,210 pounds or 550 kilograms, will intentionally collide with a small asteroid named Dimorphos. This collision will alter the space rock's orbit around its larger companion, Didymos. Astronomers will measure and assess the changes brought about by this impact, evaluating the effectiveness of kinetic impact as a method to deflect asteroids. This technique, which NASA plans to utilize in the future against asteroids posing a threat to Earth, is particularly effective when implemented well in advance. By making incremental adjustments, even small nudges can lead to significant changes over time. DART represents the first space mission designed to test this specific asteroid deflection technique, or any other of its kind. The DART probe was launched from the Vandenberg Space Force Base in California, riding aboard a SpaceX Falcon 9 rocket in late November 24. The members of the DART mission team have thoroughly examined the spacecraft's various systems, including its primary scientific instrument, a camera known as DRACO or Didymos Reconnaissance for Asteroid Camera and Optical Navigation. It's worth noting that NASA's love for abbreviations can be quite overwhelming. The DART spacecraft itself is relatively small, with its core being a box measuring barely a meter on all sides. It features two roll-out solar arrays that expand its width to around 12 meters or 40 feet. DART utilizes an electric propulsion system that generates a continuous push by emitting a stream of charged ions, ensuring a gentle and steady acceleration. The DART spacecraft is equipped with NASA's innovative xenon thruster, known as the Commercial Next-C engine, which was developed collaboratively by NASA's Glenn Research Center and the aerospace company HeroJet Rocketdyne. The Next-C engine is a solar-powered ion propulsion system that holds promise for future spacecraft applications. However, it does not serve as DART's primary propulsion system. Instead, the probe relies on 12 hydrazine thrusters to navigate its way towards the Didymos-Dimorphos pair. Nevertheless, the Next-C engine will undergo a crucial in-space test during the mission. The spacecraft will make multiple loops around Earth, utilizing its electric thruster to gain the necessary velocity to escape Earth's orbit. From there, it will set a course towards Didymos, possibly flying past another asteroid called 2001 CB21 en route. As DART approaches its target, the significance of the mission intensifies. The DRACO camera will capture the probe's first images of the Didymos system approximately 30 days prior to impact. These images will aid in refining DART's trajectory towards Dimorphos. Then, just 10 days before the planned impact, DART will deploy a small Italian spacecraft named Lycia Q. This tiny spacecraft will swiftly pass by Dimorphos immediately after the collision, observing and documenting its immediate effects. Considering DART's projected speed of around 15,000 miles per hour or 24,000 kilometers per hour at impact, the resulting effects could be quite dramatic. The impact between DART and Dimorphos will occur when the Didymos system is approximately 6.8 million miles or 11 million kilometers away from Earth. This moment marks the closest proximity of the two asteroids to our planet along their elliptical path around the Sun, and it is not a mere coincidence. The timing has been strategically chosen to enable scientists to conduct higher-quality telescopic observations of Didymos following the collision. The last time Didymos came this close to Earth was in 2003, and the next close approach will happen in 2062. Observations of Didymos and Dimorphos will persist well into the future, and not just from a distance. In a few years, the European Space Agency plans to launch a spacecraft called Hera, which will journey to the Didymos system to provide a close-up examination of the impact's aftermath. Didymos and Dimorphos serve as particularly suitable targets for DART due to their relatively small sizes. Didymos measures around 780 meters or half a mile across, while Dimorphos measures a mere 106.60 meters or 525 feet in diameter. When viewed from Earth through optical ground-based telescopes, they appear as a single point of light that fluctuates in brightness as Dimorphos orbits around Didymos. The pattern of these brightness fluctuations will change following DART's impact. It's worth noting that Didymos and Dimorphos will not come close enough to Earth to pose any unintended danger. The DART project incurred a cost of $324.5 million, with $308 million allocated to spacecraft development, $68.8 million for launch services provided by SpaceX, and an estimated $16.5 million designated for operations and data analysis. DART is expected to collide with Dimorphos at a velocity of 6.6 kilometers or 4.1 miles per second. This impact is projected to alter Dimorphos's orbital period around Didymos from 11.9 to 11.8 hours, a difference of a mere 4.2 minutes. Consequently, Dimorphos will be slightly drawn closer to Didymos. We are eager to hear your thoughts on the potential impact of an asteroid on Earth in the comments section below.